Every time you look up at the night sky, you see darkness. Between the stars, there are quiet black spaces. They look empty. They look calm. Your eyes move past them without a second thought. In 1995, a group of astronomers decided to test that darkness. They chose a small patch of sky that looked almost completely blank. No bright stars, no glowing galaxies, nothing that stood out in earlier surveys. Just a quiet, dark square between familiar stars. Then they pointed the Hubble Space Telescope at it, and they did not move it for 10 full days. This project became known as the Hubble Deep Field. The idea was simple but bold. If you stare at a truly empty patch of sky long enough, what will you find? Will it stay empty? Or will faint light begin to appear? The deep field worked like a core sample of the universe. Imagine drilling a thin cylinder into the ground to study the layers of soil. In the same way, this small square of sky was a narrow sample of everything that lies far beyond our galaxy. Earlier images of this region showed almost complete darkness. At normal exposure times, there was nothing remarkable there. That is why the team chose it. They wanted a clean test. If the region contained hidden galaxies, they would only show up after long exposure. The telescope would need to collect light slowly, one tiny photon at a time. Over 10 days, Hubble gathered more than 100 hours of exposure. It took hundreds of separate images. Each one captured faint light that human eyes could never see on their own. When those images were processed and combined, the darkness changed. The empty square filled with structure. Not a few distant stars, not a handful of faint smudges. Thousands of galaxies. Roughly 3,000 distinct galaxies appeared in that tiny patch of sky. Each small blur in the final image was not a star inside our Milky Way. It was an entire galaxy. Each galaxy contained billions of stars of its own. Most of the points of light in the deep field image are galaxies. Only a small number are faint foreground stars from our own galaxy. That means, when you look at the deep field image, you are not mostly seeing stars. You are seeing whole island universes scattered across billions of light years. And this patch of sky was tiny. Astronomers measure the sky in angles, not in miles. One full circle around you is 360 degrees. The full moon appears about half a degree wide in the sky. Each degree can be divided into 60 smaller units, called arc-minutes. The Hubble Deep Field was only about 2.6 arc-minutes across on each side. That means it was less than 1/10 of the width of the full moon. Another way to imagine it is this. Hold a grain of sand at arm's length. The part of the sky that grain would cover is about the size of the deep field. That small square represents only a tiny fraction of the entire sky. Yet inside it are thousands of galaxies. This was not just a pretty picture. It changed how many scientists and everyday people felt about space. The darkness between stars was no longer just empty space. It became something else. It became distance. It became time. It became light that was simply too faint to see without patience. The deep field showed that emptiness can be an illusion created by limits. When you do not collect enough light, space looks blank. When you wait long enough, structure appears. That first image was like opening a window in a dark room. At first, you see nothing. Then shapes begin to form. Then you realize the room was never empty at all. And this was only the beginning. Before the image could reveal thousands of galaxies, someone had to take a risk. Someone had to decide that 10 days of precious telescope time was worth spending on what looked like nothing at all. If you had control of one of the most powerful telescopes ever built, would you spend 10 days staring at darkness? That was the real question facing astronomers in the mid-1990s. The Hubble Deep Field was not just an image, it was a decision. And that decision felt risky. When the Hubble Space Telescope launched in 1990, it carried huge expectations. One of its main scientific goals was to help measure the size and age of the universe. Astronomers hoped it would refine the value of the Hubble constant, test models of cosmic expansion, and reveal how galaxies formed over time. But in its early years, Hubble struggled. A flaw in its primary mirror caused blurry images. For a while, critics questioned whether the telescope would live up to its promise. That changed in 1993. During a servicing mission, astronauts installed corrective optics and upgraded instruments, including the Wide Field and Planetary Camera 2. After that repair, Hubble began delivering sharp, detailed images of distant galaxies. Scientists suddenly realized the telescope could see much deeper into space than many had predicted before launch. This opened a new possibility. If Hubble could capture faint galaxies in normal exposures, what would happen if it stared at one small patch of sky for days at a time? Could it reveal galaxies so distant and faint that no telescope had ever recorded them? The idea was bold. Telescope time on Hubble was extremely valuable. Observing proposals from scientists around the world competed for limited hours. Every minute had to be justified. Spending 10 full days on what appeared to be an empty patch of sky felt almost reckless. Some astronomers worried that the result might show very little. If the field truly contained nothing detectable, that would mean wasting a significant portion of a year's observing time. The total observing campaign required about 10 consecutive days. That represented roughly 10% of Hubble's annual observing time at that moment. It was not a small investment. The risk was not only about time, it was also about reputation. If the deep field returned an image with only a few faint smudges, critics could argue that the gamble was unnecessary. The telescope might have been used instead for more predictable science. But there was another way to see it. Deep imaging of distant galaxies could act like a fossil record of the universe. The farther a galaxy is from us, the longer its light has traveled. Because light takes time to move through space, looking far away means looking back in time. If Hubble could detect extremely distant galaxies, astronomers could study what galaxies looked like when the universe was much younger. That would help test ideas about how galaxies grow and change over billions of years. By the early 1990s, cosmology was entering a period of rapid development. Scientists were debating key questions. How fast is the universe expanding? How many galaxies are there? Did galaxies form early and slowly evolve? Or did they merge and grow over time? A deep field could provide direct evidence. The person who helped push this idea forward was Robert Williams, the director of the Space Telescope Science Institute. He had seen early deep exposures taken with the upgraded camera. In those images, he noticed a surprising number of faint galaxies scattered across small regions. Instead of using his discretionary observing time on a single object, he chose something different. He chose emptiness. He proposed aiming Hubble at a carefully selected blank region and collecting as much light as possible. There was also a strategic element to the plan. The data would be released quickly to the public scientific community. That meant researchers around the world could analyze the image and publish results. It would not belong to a single small team. This approach increased excitement and reduced resistance. Even those who questioned the gamble could see the value in open access to a deep cosmic sample. Still, uncertainty remained. Stacking hundreds of exposures does not guarantee discovery. Noise can build up. Background glow from space can interfere. Cosmic rays can strike the detector. There was no promise that thousands of galaxies would appear. All they knew was that faint objects require patience. So the deep field was approved. 10 days were set aside. Hundreds of exposures were planned. Filters were selected. The region of sky would be chosen carefully to avoid bright stars and known galaxies. The telescope would stare. The next step was to find a patch of sky quiet enough to test the idea properly. It could not just be dark. It had to be clean, stable, and free from bright foreground distractions. Choosing nothing turned out to require careful precision. Before Hubble could stare into darkness, the team needed to answer a very specific question. Where exactly is nothing? The sky may look empty to our eyes, but astronomers know that most regions contain stars, gas, dust, or distant galaxies. If the deep field was going to work, the target area had to meet strict conditions. First, it needed to be far away from the crowded plane of our own galaxy, the Milky Way. The Milky Way forms a thick band of stars and dust across the sky. If Hubble pointed near that band, faint distant galaxies could be hidden behind foreground stars or blocked by interstellar dust. So the team chose a region at high galactic latitude. That simply means it sits well above the crowded middle of our galaxy, where there are fewer nearby stars and less dust. Second, the field needed to avoid bright foreground stars. Even one bright star can create glare, scatter light, and saturate parts of the detector. That glare would drown out the faint signals from distant galaxies. The deep field needed to be dark not just to the eye, but also free of strong nearby light sources. Third, the region had to be stable for observation. Hubble orbits Earth. That means Earth, the Sun, and the Moon can sometimes block or interfere with certain directions in the sky. The team needed a location that could be observed continuously for long periods without interruption. They chose a region in the northern constellation Ursa Major, near the handle of the Big Dipper. This area falls within what astronomers call Hubble's continuous viewing zone. That means Hubble can observe it for extended periods during each orbit without Earth blocking the view. The exact coordinates were carefully recorded. Astronomers use a coordinate system similar to latitude and longitude on Earth. Instead of north and south, they use declination. Instead of east and west, they use right ascension. The center of the Hubble Deep Field was set at right ascension 12 hours, 36 minutes, 49.4 seconds. Declination plus 62 degrees, 12 arc minutes, 58 arc seconds. These numbers act like a precise map pin on the sky. The team also checked other wavelength surveys before finalizing the location. They examined infrared, ultraviolet, X-ray, and radio maps. to ensure there were no strong hidden sources that might interfere. If a region showed bright emissions in radio or X-ray light, it could signal active galaxies or quasars that would dominate the field. They wanted a clean cosmic background. Radio observations were used to rule out fields containing bright radio galaxies. This reduced the chance of including powerful active galactic nuclei that could overwhelm faint surrounding objects. The selection process took time. It was not random. It required cross-checking catalogs and carefully eliminating candidate regions that did not meet the strict criteria. In the end, the chosen patch looked almost completely blank in previous sky surveys. At standard exposure times, nothing remarkable stood out. No obvious galaxies, no glowing nebulae, no bright stars. This was exactly what they wanted. The deep field would only work if the region appeared empty under ordinary viewing conditions. That way, any discoveries would come purely from depth, not from targeting something already known. The size of the region was also deliberate. It measured about 2.6 arc-minutes on each side. Earlier, we explained that an arc-minute is 1/60th of a degree. For comparison, the full moon appears about 30 arc-minutes across in the sky. That means the deep field was less than 1/10 the width of the moon. In fact, the area covers only about 1/24 millionth of the entire sky. Imagine dividing the whole sky into 24 million tiny squares. The deep field would be just one of them. And yet, this single square would soon reveal thousands of galaxies. That scale is important. If such a tiny region could contain so much structure, what does that suggest about the rest of the sky? What might exist in every other quiet patch between the stars? But before any galaxies could appear, the telescope had to begin its long stare. The location was chosen. The coordinates were locked in. The filters were selected. The schedule was approved. Now came the hardest part. Hubble would collect light slowly, patiently, and repeatedly. The darkness was ready to be tested. Once the location was chosen, the next step was simple in theory and demanding in practice. Hubble had to stare. The observations for the Hubble Deep Field took place between December 18th and December 28th, 1995. While many people were thinking about holidays, the Hubble Space Telescope was quietly collecting faint light from a tiny square in Ursa Major. The plan was not to take one single long photograph. Instead, the team divided the observing time into many shorter exposures. In total, Hubble captured 342 separate images during the campaign. When combined, these exposures added up to more than 100 hours of total observing time. Why not just take one extremely long exposure? There are practical reasons. Cosmic rays constantly strike the detector in space. These high-energy particles leave bright streaks or dots in an image. If the team had taken one giant exposure, those cosmic ray hits would have permanently damaged parts of the frame. By splitting the observation into many shorter images, scientists could compare frames and remove unwanted streaks later. Shorter exposures also reduce the risk of losing all the data if something unexpected happens. If a problem interrupts one exposure, only that frame is lost, not the entire project. The instrument used for the deep field was the Wide Field and Planetary Camera 2, often called WFPC-2. This camera had been installed during the 1993 servicing mission and was equipped with corrective optics that fixed Hubble's earlier mirror problem. WFPC-2 was made up of 4 separate CCD cameras. These cameras recorded light as digital signals. Each pixel collected photons and turned them into measurable electronic counts. The deep field used 4 different filters. Each filter allowed only certain wavelengths of light to pass through. The filters covered a wide range of wavelengths, from near ultraviolet to near infrared. Specifically, they included filters centered around approximately 300 nanometers, 450 nanometers, 606 nanometers, and 814 nanometers. The near ultraviolet filter at 300 nanometers had lower sensitivity, but it helped detect very blue galaxies, which often contain young, hot stars. The 450 nanometer filter corresponds roughly to blue light. The 606 nanometer filter captures green to yellow light. The 814 nanometer filter captures red to near infrared light. Using multiple filters allowed astronomers to measure color differences between galaxies. Those colors later helped estimate distances and ages. Each exposure was carefully scheduled. Because Hubble orbits Earth, it cannot observe continuously without interruption. During parts of each orbit, Earth blocks the telescope's view of a target. So the observing plan was arranged to maximize usable viewing time whenever the field was visible. The field also sat in Hubble's continuous viewing zone. This meant that for much of the orbit, the telescope could look at the region without Earth getting in the way. That allowed longer stretches of uninterrupted exposure. During the 10-day campaign, Hubble repeatedly returned to the same coordinates, gathering photons that had traveled for billions of years before reaching the telescope's mirror. Some of those photons were incredibly faint. A distant galaxy might deliver only a few photons during a single exposure. That is why stacking was so important. When multiple exposures are combined, faint signals add together. Noise, which is more random, does not grow in the same way. Over time, the true light from distant galaxies begins to stand out. This is similar to listening for a whisper in a quiet room. If someone whispers once, you may not hear it clearly. If they repeat the whisper many times, you begin to recognize the pattern. That is what Hubble was doing. It was listening for whispers of light from the early universe. The team also used a technique called dithering. Between exposures, Hubble's pointing was shifted by very small amounts. This slight movement allowed each part of the sky to fall on different pixels of the detector. Later, when the images were aligned and combined, this technique improved resolution and reduced the effects of defective pixels. The shifts were tiny, but they mattered. By the end of the observing campaign, Hubble had gathered a deep stack of images in 4 colors, covering one of the darkest patches of sky available. Still, what came out of the camera at first did not look like the famous deep field image we know today. The raw data contained noise, streaks from cosmic rays, scattered light patterns, and subtle background variations. Before the universe could be revealed, the data had to be cleaned, aligned, and carefully processed. The darkness had been recorded. Now it needed to be understood. When the observing campaign ended, the telescope had done its job. But the image we recognize today did not appear instantly. What Hubble sent back to Earth were hundreds of separate frames. Each one contained faint light, but also noise. Some pixels were struck by cosmic rays. Some exposures had subtle background patterns. A few contained streaks from small bits of space debris passing through the field of view. The first step was cleaning. Because the team had taken many shorter exposures instead of one long one, they could compare frames taken close together. If a bright dot appeared in only one image and not in the others, it was likely caused by a cosmic ray. Those pixels could be identified and removed. This method worked because real galaxies remain in the same place from frame to frame. Random particle strikes do not. The team also removed faint trails left by satellites or debris. Even in space, stray reflections and moving objects can leave marks in an image. Another challenge came from scattered sunlight. Sometimes, faint light from Earth's edge enters the telescope and creates soft patterns across the detector. In some of the deep field exposures, this scattered light formed faint X-shaped patterns. These had to be modeled and subtracted carefully so they would not interfere with faint galaxy detection. Once the obvious noise and artifacts were removed, the next step was alignment. Remember that the telescope was slightly shifted between exposures. This was done on purpose to improve detail. Now those tiny shifts had to be corrected digitally. Each frame was lined up so that stars and galaxies matched perfectly from image to image. After alignment, the exposures were combined. This combining process is often called stacking. Stacking works because faint light adds together. If a distant galaxy sends only a few photons per exposure, stacking hundreds of exposures strengthens its signal. The more exposures combined, the clearer that faint galaxy becomes. Noise behaves differently. Because noise is more random, it does not increase at the same rate as true signal. Over time, the signal stands out, while noise fades into the background. The team used a processing method known as the drizzle algorithm. This technique allowed them to merge the slightly shifted exposures onto a finer grid of pixels. The result improved resolution beyond what a single frame could achieve. After cleaning, aligning, and stacking, the final image began to take shape. At first glance, the result looked almost unreal. The small square that had appeared dark in earlier surveys was now filled with points of light. Not a few, thousands. Most of the visible objects in the final deep field image are galaxies. Only a handful are faint stars from our own Milky Way galaxy. Each tiny smudge represents an entire galaxy containing billions of stars. Some galaxies appear spiral with faint curved arms. Some appear smooth and round. Others look irregular, clumpy, or stretched, possibly due to interactions with neighboring galaxies. The color of each galaxy also tells part of the story. After the separate exposures in different filters were combined, a color composite was created. Light collected at longer wavelengths was assigned red tones. Light at medium wavelengths was assigned green. Shorter wavelengths were assigned blue. This color mapping helps the human eye see differences that would otherwise be invisible in grayscale. Bluer galaxies often contain younger, hotter stars. Redder galaxies may contain older stars, or may be so distant that their light has been stretched toward red wavelengths as it traveled through the expanding universe. Some galaxies in the deep field are extremely faint, A few approach what astronomers call 30th magnitude. That is billions of times fainter than the faintest stars visible to the naked eye. When the processed image was finally revealed to the scientific community, the reaction was immediate. A region once labeled empty now appeared crowded. The darkness between bright stars was not empty at all. It was filled with distant island universes. And this was only the first deep field. What the team had done in 1995 opened the door to even deeper observations in the years that followed. If 10 days revealed thousands of galaxies, what might 11 days reveal? Or thousands of hours combined across decades? The image that changed our view of the universe had arrived. But its implications were just beginning to unfold. Hold a grain of sand at arm's length. Now imagine that tiny speck covering a piece of the night sky. That is the feeling of the Hubble Deep Field. It sounds simple, but that comparison matters. The deep field was not a wide panorama. It was not a sweeping view across the Milky Way. It was a very small, carefully chosen square of darkness. Astronomers measure the sky using angles, not miles. The sky surrounds us like the inside of a giant sphere. To describe positions and sizes on that sphere, scientists divide it into degrees. A full circle contains 360 degrees. Each degree is divided into 60 smaller units called arcminutes. And each arcminute is divided again into 60 arcseconds. The Hubble Deep Field measures about 2.6 arcminutes on each side. That number may not mean much at first, so let's compare it to something familiar. The full moon appears about 30 arcminutes wide in the sky. That means the deep field is less than 1/10 the width of the moon. If you could line up about 12 deep fields side by side, they would stretch across the moon's visible disk. Another helpful image is this. Hold a small pin at arm's length. The tiny circle that pin covers in the sky would be close to the size of the deep field. It is so small that your eye would never notice it as special. You could scan that patch with binoculars and see almost nothing unusual. And yet, inside that tiny square are thousands of galaxies. The deep field covers about 0.0011 square degrees. The entire sky covers about 41,253 square degrees. If you divided the whole sky into equal squares the size of the deep field, you would need around 24 million of them to cover everything. That means the deep field represents about 1/24 millionth of the sky. 1 out of 24 million. Pause for a moment and imagine dividing the sky into 24 million tiny windows. Hubble opened just one of those windows. And in that one small opening, it revealed roughly 3,000 galaxies. That is the scale shock. Before this image, astronomers already believed that galaxies filled the universe. But belief feels different from seeing. When people saw the deep field image, they understood something new. The darkness between bright stars is not empty space. It is distance. When you look up at the night sky, most of the stars you see belong to our own galaxy. They are relatively close in cosmic terms. Beyond them lies a vast background that appears black to the eye. But that blackness is not a blank wall. It is a curtain hiding faint light. The deep field peeled back that curtain. At normal exposure times, earlier surveys showed almost complete darkness in that region. There were no bright galaxies, no glowing clouds, nothing obvious to draw attention. That was exactly why astronomers chose it. If you aim at something already bright, you only confirm what you know. If you aim at darkness, you test the limits of your instrument. The deep field acted like a cosmic core sample. Imagine drilling into the Earth and pulling up a thin column of rock. From that narrow sample, you learn about layers deep underground. In the same way, this tiny patch of sky became a sample of the distant universe, and the sample showed abundance. Thousands of galaxies packed into a region smaller than a grain of sand at arm's length. Each galaxy containing billions of stars. Each star shining with its own planets, its own possible stories. All hidden inside what once looked like nothing. This scale changes perspective. If 1/24 millionth of the sky contains thousands of galaxies, what about the rest? It suggests that nearly every dark patch you see at night hides countless distant systems. The sky appears empty only because our eyes and short exposures cannot gather enough light. Imagine 24 million multiplied by 3,000. Using this extremely simplified math, that's at least 72 billion galaxies. And we live in one of them. What are the chances life on Earth is all there is? Think about that. That smallness also explains something else. When you observe such a tiny area, and the objects inside it are extremely faint, you cannot rush the process. Each distant galaxy sends only a thin stream of photons toward Earth. The farther away the galaxy, the weaker that stream becomes. To draw shapes from that faint light, the telescope must collect photons patiently over many hours. A window that small needs a very long stare to gather enough light to draw shapes. Late December 1995. While many people were focused on the holidays, the Hubble Space Telescope began a long, quiet watch. The target was already chosen. The coordinates were locked in. Now the telescope had one job: stare. The Hubble Deep Field observations ran from December 18th to December 28th, 1995. For 10 straight days, the telescope repeatedly pointed at the same tiny square in the constellation Ursa Major. But 10 days does not mean one continuous photograph. Hubble orbits Earth roughly once every 96 minutes. During each orbit, part of the time the telescope can see its target, and part of the time Earth blocks the view. So the deep field was built piece by piece, orbit by orbit. Over the course of those 10 days, Hubble captured 342 separate exposures. Each exposure lasted a limited amount of time. Then the telescope shifted slightly or waited for the next clear viewing window. Slowly, frame by frame, light accumulated. When all those exposures were added together, the total observing time reached more than 100 hours. More than 100 hours focused on a region that earlier surveys had labeled almost empty. That is why the project felt risky. Telescope time is one of the most valuable resources in astronomy. Scientists around the world compete for it. Every hour must be justified with clear scientific goals. The deep field tied up about 10% of Hubble's annual observing time during that period. That is not a small commitment. If the result had shown only a few faint smudges, critics might have questioned the decision. The telescope could have been used to study known galaxies, star-forming regions, or other high-profile targets. Instead, it stared at darkness. The strategy behind the long exposure was simple in principle. Faint objects require time. A distant galaxy may send only a few photons toward the telescope during a short exposure. Those few photons are not enough to form a clear image. But if you gather photons over many hours, the signal slowly builds. It is like filling a bucket with slow drips of water. One drip does not change much, but over time, the bucket fills. That is what those 342 exposures were doing. They were collecting faint drips of light from galaxies billions of light years away. The timing of the observation also mattered. The chosen region lies in what astronomers call Hubble's continuous viewing zone. That means the telescope could observe it for long stretches without Earth blocking the view. This allowed the team to maximize the amount of usable observing time during each orbit. Even so, the schedule required careful planning. Each exposure had to be timed precisely. The telescope's pointing had to remain steady. The instrument settings had to switch between filters in a coordinated sequence. And this was happening in space, hundreds of kilometers above Earth. While the telescope was watching, no one could intervene directly. Commands were uploaded in advance. The spacecraft followed its programmed instructions. Every exposure added another thin layer of information. During those 10 days, the telescope was not chasing bright fireworks. It was listening for whispers. And there was always uncertainty. Would stacking these exposures truly reveal something new? Would noise overwhelm the faint signals? Would cosmic rays damage too many frames? The team would not know until the data were processed. But the clock kept ticking. Orbit after orbit, night after night. The same patch of darkness. By the time December 28th arrived, Hubble had gathered one of the deepest optical datasets ever recorded at that time. The calendar says 10 days. The exposure log says 342 frames. The combined total says more than 100 hours of collected light. But the real story is not just about time. It is about how that time was used. Because the camera and the filters chosen for this project were just as important as the hours themselves. The calendar tells us 10 days, yet the camera story is really about instruments and filters. Hubble is the telescope, but the camera is the eye. For the deep field, that eye was an instrument called the Wide Field and Planetary Camera 2. To keep things simple, think of it this way. The telescope gathers light. The camera records it. This camera had been installed during a servicing mission in 1993. Before that mission, Hubble's mirror had a flaw that caused blurry images. Astronauts corrected that problem and upgraded the imaging system. After the repair, the telescope began delivering sharp, detailed pictures of distant galaxies. The deep field would not have been possible without that upgrade. The Wide Field and Planetary Camera 2 was not a single detector. It actually contained 4 separate imaging sensors arranged together. 3 of them covered a wide field of view. The 4th offered slightly different imaging characteristics. Each sensor used a device called a charge-coupled device, or CCD. To avoid too many acronyms, think of a CCD simply as a light sensor made up of tiny squares called pixels. Each pixel collects incoming light and turns it into a digital signal. When photons from distant galaxies hit the detector, they create small electrical charges. Those charges are measured and stored as numbers. After many photons arrive, a faint object begins to form in the data. But capturing light is only part of the process. The deep field did not use just one type of light. It used several. The team selected 4 broad filters. Each filter allowed only certain wavelengths of light to pass through. One filter captured near ultraviolet light, centered around 300 nanometers. This wavelength is shorter than visible blue light and has lower sensitivity, but it helps identify very blue, young galaxies that contain hot stars. Another filter captured light around 450 nanometers, which appears blue to our eyes. A third filter captured light around 606 nanometers, which falls in the green to yellow part of the visible spectrum. The fourth filter captured light around 814 nanometers, which is in the red to near infrared range. Why use 4 filters instead of 1? Because color carries information. Different galaxies shine more brightly at different wavelengths. Young galaxies filled with hot, massive stars tend to appear bluer. Older galaxies with cooler stars often appear redder. Very distant galaxies can also appear red because their light has been stretched as the universe expands. By recording the deep field in multiple wavelengths, astronomers could later estimate distances and ages using color differences. The filters were used in a carefully planned sequence. During the 10-day campaign, the telescope switched between them, collecting exposure after exposure in each wavelength band. The near ultraviolet filter was less sensitive than the others, meaning it required longer exposure times to gather enough light. Even so, including it helped identify certain types of galaxies that might otherwise blend into the background. The combination of these filters created a wide spectral coverage from near ultraviolet through visible light and into near infrared. This range was important. Galaxies at moderate distances shine strongly in visible light. Very distant galaxies, whose light has been stretched to longer wavelengths, may shine more strongly in the red and near infrared. By covering this range, the deep field could detect galaxies across a wide span of distances. The camera also had to maintain stability. During each exposure, Hubble had to hold its position extremely steady. Even tiny movements could blur faint objects. The telescope's pointing system used guide stars to keep it locked onto the target. Every photon collected during those exposures passed through the mirror, through the filter, and onto the detector. And each photon had traveled for millions or billions of years before reaching the telescope. The filters determined the colors. The camera determined the clarity. The exposure time determined the depth. Individually, each short exposure might not look impressive, but together they would reveal something far beyond what a single snapshot could show. The filters set the colors, and the strategy sets the depth. Many short looks become one long look. One raindrop on your hand feels small. 1,000 raindrops becomes a stream. That is the idea behind stacking. When Hubble observed the deep field, it did not take one single continuous image for 100 hours. That would have been risky and impractical. Instead, it took hundreds of shorter exposures and combined them later. This approach is called stacking. Each individual exposure collected a small amount of light from distant galaxies. In many cases, a galaxy might send only a few photons to the detector during one exposure. Those few photons are not enough to create a clear shape on their own. But when you add hundreds of exposures together, those photons accumulate. Signal builds. Noise behaves differently. In any image, there is always background noise. Some of it comes from the detector electronics. Some comes from faint background light in space. Some comes from random particle strikes. Noise tends to vary randomly from frame to frame. When multiple exposures are combined, true signals that appear in the same position in every image grow stronger. Random noise does not add up in the same organized way. This improves what scientists call the signal-to-noise ratio. You can think of it like listening for a quiet sound in a noisy room. If someone whispers once, it might be lost in background chatter. If they repeat the whisper over and over in the same rhythm, your brain begins to recognize the pattern. The repeated signal stands out. Stacking works in a similar way. Each exposure was carefully aligned so that stars and galaxies overlapped precisely. Once aligned, the images were added together. With every added frame, faint galaxies became clearer. This method allowed Hubble to see objects far fainter than what would be visible in a single exposure. Some galaxies in the deep field approach what astronomers call 30th magnitude. That is billions of times fainter than the faintest stars you can see with your eyes. Without stacking, those galaxies would remain invisible. Splitting the observation into many shorter exposures also had practical benefits. Cosmic rays strike the detector frequently. These high-energy particles create bright spots or streaks in individual frames. If the entire deep field had been captured in one exposure, cosmic ray damage would have permanently affected the image. By using many shorter exposures, scientists could identify which bright pixels appeared in only one frame. Those were likely caused by cosmic rays. They could then remove those pixels during processing. Stacking also allowed the team to correct for small shifts in the telescope's pointing. Between exposures, the telescope was moved slightly on purpose. This technique helped improve resolution later during processing. Each short exposure captured the same region of sky, but with tiny differences in alignment. When these were combined carefully, the final image became sharper than any single frame could achieve. The core principle behind stacking is simple. The longer you observe, the fainter you can see. Every additional hour of exposure allows the telescope to collect more photons from distant galaxies. Those photons have traveled for billions of years. They arrive slowly and sparsely. Time is the key. Stacking turned 10 days of observation into a single deep window through space and time. Instead of seeing only the brightest nearby galaxies, Hubble could detect distant systems that had never been observed before. It is important to remember that stacking does not invent new objects. It does not create galaxies that are not there. It simply reveals what was always present, but too faint to detect quickly. The darkness between bright stars is filled with distant light. It just takes patience to see it. Stacking created depth, but depth alone does not guarantee sharpness. To sharpen the final image even further, the team used another subtle technique. Tiny shifts in pointing would help turn many exposures into something clearer than expected. A painter does not always drag the brush in one long stroke. Sometimes they tap the brush gently in slightly different spots, layering color until the surface looks smooth and detailed. The Hubble Deep Field used a similar idea. Between exposures, the Hubble Space Telescope did not stay perfectly locked on one exact pixel position. Instead, it shifted its pointing by very small amounts. This technique is called dithering. The shifts were tiny, so small that they would not be noticeable without careful measurement. But those small movements made a big difference in the final result. To understand why, think about how the camera records light. The imaging detector is made of many small square pixels. Each pixel collects photons and turns them into digital values. But each pixel has a fixed position and size. If the telescope stayed perfectly still for every exposure, each galaxy would always fall on exactly the same pixels. Any small defects in those pixels would affect the final image in the same way every time. Pixels can have slight differences in sensitivity. Some may respond a little more strongly, others a little less. A few may be slightly damaged or noisy. By shifting the telescope's pointing slightly between exposures, each part of the sky falls on different pixels over time. That means a faint galaxy might land on one set of pixels during the first exposure, and a slightly different set during the next. Later, when the exposures are aligned and combined, these tiny shifts allow scientists to average out pixel imperfections. Dithering also improves resolution. Resolution describes how finely an image can show detail. Each pixel has a certain size in the sky. For the original camera setup, the pixel scale was about 0.09 arc-seconds per pixel. An arc-second is a very small angular measurement. There are 60 arc-seconds in 1 arc-minute and 60 arc-minutes in 1 degree. So 0.09 arc-seconds is extremely small. Even so, some distant galaxies are so tiny that their structure falls between pixel boundaries. When the telescope shifts slightly between exposures, it samples the image at slightly different positions. Later, these slightly offset samples can be combined using a processing method called drizzling. Drizzling takes the dithered exposures and maps them onto a finer output grid. Instead of being limited by the original pixel spacing, the final image can represent details at a smaller scale. For the deep field, the final processed image reached an effective pixel scale of about 0.040 arc-seconds per pixel. That is more than twice as fine as the original 0.09 arc-seconds per pixel scale. This does not break the laws of physics. The telescope still has limits set by its mirror size and optical design. But dithering and careful processing allow scientists to recover more detail than a single fixed exposure would provide. Imagine looking at a distant object through a screen door. If you keep your eyes still, the grid pattern blocks certain details. But if you move your head slightly and combine what you see from each position, you can mentally fill in more of the image. That is what dithering does for the camera. Each exposure captured the same region of sky, but from a slightly shifted position. When combined, those exposures created a sharper and cleaner final picture. This technique was especially important for the deep field because many of the galaxies are extremely small and faint. Some appear as tiny smudges only a few pixels across in a single frame. Without dithering, their shapes might blur into noise. With dithering and drizzling, faint spirals, irregular clumps, and merging systems became clearer. The improvement was subtle but meaningful. The deep field image that the world saw was not just the result of long exposure time. It was also the result of careful motion planning and advanced data processing. Tiny shifts in pointing, repeated hundreds of times, help turn a faint signal into a detailed map of distant galaxies. After the camera gathers light and the pointing adds detail, the data still carries scars from space itself. A raw space image is rarely clean. Space keeps interrupting. When the Hubble Deep Field observations finished, the data did not look like the famous final image. Instead, it looked messy. Bright streaks crossed some frames. Random white dots appeared in others. Faint patterns floated across parts of the detector. None of that was coming from distant galaxies. It was noise. One of the biggest challenges came from cosmic rays. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. When one of these particles strikes the camera's detector, it creates a bright pixel or streak. In a single exposure, that bright mark can look like a star or a tiny galaxy. But cosmic rays are random. They hit different pixels in different exposures. That randomness is the key to removing them. Because the deep field was built from 342 separate exposures, scientists could compare frames taken close together in time. If a bright spot appeared in only one image, but not in the others, it was almost certainly caused by a cosmic ray. Those pixels were flagged and removed during processing. If the project had relied on one single long exposure, those cosmic ray marks would have permanently damaged the image. Splitting the observation into many shorter exposures made cleanup possible. Cosmic rays were not the only interruptions. Sometimes small pieces of space debris or satellites pass through the field of view. These objects can leave faint trails across an exposure. Like cosmic rays, these trails usually appear in only one frame. Again, by comparing exposures, scientists could identify and mask those streaks. Another complication came from scattered sunlight. Hubble orbits Earth. Even though it looks outward into space, faint light from Earth's atmosphere can sometimes scatter into the telescope. In some deep field exposures, this scattered light created faint X-shaped patterns across the image. These patterns were subtle, but they could interfere with faint galaxy detection if left uncorrected. To remove them, scientists carefully modeled the background light pattern in each affected exposure. They smoothed the image to isolate large-scale brightness variations, then subtracted those patterns from the data. This process required patience and precision. You cannot simply erase bright areas without risking damage to real faint objects. The team had to make sure they were removing only unwanted background effects, not distant galaxies. After cosmic rays, satellite trails, and scattered light were handled, the images still contain normal background noise. Every detector produces a small amount of electronic noise. Even in total darkness, a camera sensor generates faint signals due to thermal and electronic effects. These signals had to be measured and subtracted carefully. Calibration frames were used to account for these effects. Scientists measured how the detector behaves when no light is entering it. Then they corrected the deep field exposures accordingly. This stage of processing may sound technical, but it is essential. If you want to see objects that are billions of times fainter than what the human eye can detect, you must remove every source of false signal. Only after cleaning could the true faint light from distant galaxies stand out clearly. Think of it like polishing a window. If the glass is covered in dust and streaks, the view outside looks blurry and distorted. Clean the glass carefully, and the outside world becomes sharper. The deep field required that kind of cleaning. Hundreds of exposures had to be examined, compared, and corrected. Every cosmic ray mark removed. Every streak masked. Every background pattern smoothed and subtracted. Only then could the stacking process combine the cleaned frames into a single deep image. The messy raw data slowly transformed into a quiet, structured view of the distant universe. Cleaning removes the noise, and drizzling gathers the cleaned frames into a single, deeper window. Drizzling isn't just a way to add dressing to your salad. It's also a way to line up many slightly shifted images and rebuild detail. After cosmic rays were removed and background patterns were corrected, the deep field exposures were clean, but they were still separate frames. Hundreds of individual images needed to become one unified picture. That is where drizzling came in. Earlier, we explained that the telescope was moved slightly between exposures. Those tiny shifts were called dithering. Each exposure sampled the sky at a slightly different position on the detector. Now those small shifts became an advantage. The drizzle algorithm takes each cleaned exposure and maps it onto a common output grid. Instead of simply stacking pixels directly on top of one another, drizzling accounts for the tiny offsets between frames. Imagine placing transparent sheets on top of each other, but each sheet is shifted by a tiny amount. If you align them carefully, you can recover finer detail than any single sheet shows on its own. Drizzling works in a similar way. Each exposure is slightly resampled and placed onto a finer grid. The light from each pixel is redistributed across the output image in a controlled way. This process preserves brightness while improving spatial sampling. The original pixel scale of the camera was about 0.09 arc-seconds per pixel. After drizzling, the final image achieved an effective pixel scale of about 0.040 arc-seconds per pixel. That means each pixel in the final image represents a smaller portion of the sky than in the original frames. This does not magically increase the telescope's mirror size. The laws of optics still apply. But by combining slightly offset exposures, scientists can reconstruct more detail than a single static image would allow. The result is a sharper and cleaner view of extremely faint galaxies. Drizzling also improves the signal-to-noise ratio. When multiple exposures are combined, faint light from distant galaxies strengthens. Noise, which varies randomly, averages out. The final image becomes smoother and clearer. The deep field image that the world saw was the product of this careful merging. Hundreds of exposures, tiny shifts in pointing, precise alignment, mathematical reconstruction. The darkness slowly transformed into structure. At this stage, the image was still in grayscale. Each filter produced its own monochrome frame. In black and white, the deep field already looked powerful. Thousands of faint smudges filled the small square. But to understand what those smudges meant, color was essential. The deep field looks like art, yet every color carries physics. Each of the 4 filters captured light at a different range of wavelengths. After drizzling was complete for each filter, scientists had 4 deep monochrome images. To create the final color image, those monochrome images were combined. Light captured at 814 nanometers was assigned red tones. Light captured at 606 nanometers was assigned green tones. Light captured at 450 nanometers was assigned blue tones. The 300 nanometer ultraviolet data was sometimes left out of the final public composite because it had lower sensitivity and contributed less visible signal. Still, it played a role in scientific analysis. When these color channels were layered together, the deep field became more than a collection of faint dots. It became a map of galaxy properties. The colors are not random decoration. They reflect how much light each galaxy emits at different wavelengths. Bluer galaxies often contain young, hot stars. These stars burn brightly and emit more short wavelength light. Redder galaxies may contain older stars, or they may be so distant that their light has been stretched by the expansion of the universe, shifting it toward longer, redder wavelengths. The final composite image approximates true color as seen by human eyes, while also stretching brightness levels so faint objects can be visible. In reality, many of these galaxies are far too faint for human vision. The image is carefully adjusted so we can see structures that would otherwise remain invisible. When the processing was complete, the deep field appeared as a tapestry of tiny galaxies, each one colored according to its light. The once empty patch filled with reds, blues, and faint golden glows. Now we can finally answer the main mystery: what appeared inside the darkness? The processed image comes into focus, and the empty patch fills with structure. At first glance, it almost feels unreal. The square that once looked dark and unremarkable now contains thousands of tiny points and smudges of light. The black background is no longer empty. It is crowded. Almost every object in the Hubble Deep Field image is a galaxy. Only a few faint points are stars from our own Milky Way. You can sometimes tell which are stars because they show subtle diffraction spikes, thin lines that extend outward due to the telescope's optics. Most of the small glowing shapes, however, are entire galaxies far beyond our own. The final deep field revealed on the order of 3,000 distinct galaxies within that tiny square of sky. 3,000 galaxies, in an area smaller than a grain of sand held at arm's length. When the first versions of the image were discussed publicly, scientists mentioned several hundred previously unseen galaxies. That was before full processing and careful counting were complete. As the data were analyzed more thoroughly, the number rose into the thousands. It is important to understand what that means. Each of those faint smudges contains billions of stars. Each star may have planets. Each galaxy may contain black holes, nebulae, clusters, and complex structures. All of that hidden inside a patch that earlier surveys described as essentially empty. This was the emotional impact of the deep field. For decades, astronomers had known that galaxies filled the universe, but seeing thousands appear in a place once labeled nothing changed the feeling of space. Darkness was no longer absence. It was depth. The deep field did not show a single bright, dramatic galaxy dominating the frame. Instead, it showed variety. Some galaxies appear large and well-formed, with spiral arms that curve gently around a bright center. These are usually closer galaxies, where the telescope can resolve structure more clearly. Others appear smooth and rounded, similar to elliptical galaxies seen nearby. But many of the distant galaxies look small and irregular. Some appear clumpy, like scattered pieces of light loosely held together. Others look stretched or distorted. A few appear to be interacting pairs, possibly merging systems in the process of combining. This variety has been described as a cosmic zoo. The shapes tell a story. Nearby galaxies often appear orderly and well-structured. Their spiral arms are defined. Their centers are bright and stable. Many distant galaxies in the deep field look less organized. Their shapes suggest active formation and frequent mergers. This supports the idea that galaxies grow over time through collisions and accumulation of smaller systems. In other words, when we look deeper into space, we are looking further back in time. And earlier galaxies appear more chaotic because the universe itself was younger and more dynamic. Brightness also varies widely across the image. Some galaxies glow clearly, even in a small portion of the frame. Others are barely visible, appearing as faint red or blue smudges. A few galaxies in the deep field approach what astronomers call 30th magnitude. That means they are billions of times fainter than the faintest stars visible to the naked eye. Without long exposure and stacking, these galaxies would remain invisible. The deep field also showed that the universe is not evenly filled in a simple way. Some areas contain clusters of galaxies close together. Other areas appear slightly less dense. Even in this tiny sample, structure begins to emerge. The most striking realization, however, is scale. If roughly 3,000 galaxies exist in 1/24 millionth of the sky, then the entire sky must contain enormous numbers of galaxies. The deep field did not directly count them all, but it provided a sample. And that sample suggested abundance beyond everyday imagination. The empty patch became proof that the darkness between stars is filled with distant island universes. Once the count lands, the next question rises naturally. How far away are these galaxies? And if they are far away, how far back in time are we seeing? Distance tells time. And in the deep field, we are looking deep into cosmic history. When you see far, you see back in time. That simple idea sits at the heart of the Hubble Deep Field. Light does not travel instantly. It moves at a fixed speed, about 300,000 kilometers per second. That sounds incredibly fast. But the universe is much larger than we instinctively imagine. When light leaves a distant galaxy, it begins a journey across space. If that galaxy is 1 billion light years away, the light takes 1 billion years to reach us. If it is 10 billion light years away, the light takes 10 billion years. So when Hubble detected faint galaxies in the deep field, it was not seeing them as they are today. It was seeing them as they were long ago. Astronomers use a measurement called redshift to describe how much the light from a galaxy has been stretched during its journey. As the universe expands, space itself stretches. When light travels through expanding space, its wavelength stretches as well. Shorter wavelengths shift toward longer, redder wavelengths. The more distant a galaxy is, the greater this redshift tends to be. In the deep field, galaxies span a wide range of redshift values. Many of the galaxies lie at moderate redshifts around 0.5 to 1. That means their light has been traveling for billions of years, but not all the way back to the earliest times. At these distances, we see galaxies during an era when the universe was younger than today, but already well developed. Some galaxies in the deep field lie much farther away. Early analysis identified candidates with redshift values greater than 5. A redshift above 5 corresponds to a time when the universe was roughly 1 billion years old. Considering that the universe is about 13.8 billion years old today, that means the light from those galaxies began its journey more than 12 billion years ago. Later follow-up observations using infrared instruments on Hubble found galaxies around redshift 6 or even higher. These galaxies are described as being more than 12 billion light-years away. In other words, the deep field includes galaxies from relatively nearby cosmic neighborhoods all the way back toward the early epochs of galaxy formation. This wide range of redshifts means the deep field is not just a snapshot of one moment in time. It is a layered image. Nearby galaxies show what mature systems look like. More distant galaxies show what younger systems looked like. The deeper you look in the image, the further back you are seeing. This is sometimes described as a time machine effect. You cannot travel physically into the past, but by looking far enough into space, you observe ancient light. Some of the faint red galaxies in the deep field are so distant that their visible light has been stretched into longer wavelengths. What was once ultraviolet or blue light when it left the galaxy may arrive at Earth as red or near infrared light. That stretching is not just a color change. It carries information about the expansion of the universe. By measuring redshift, astronomers can estimate distance. By combining distance with models of cosmic expansion, they can estimate the age of the universe at the time that light was emitted. The deep field therefore helped refine our understanding of cosmic history. It confirmed that galaxies existed when the universe was only a small fraction of its current age. It showed that even in the first billion years, galaxy formation was already underway, and it revealed that the universe is structured across vast distances. The galaxies in the deep field are not randomly placed points of light. They represent different stages of growth across cosmic time. Some appear mature and organized. Others appear irregular and clumpy, suggesting early formation and active merging. By looking at their shapes and colors together with their redshifts, astronomers can build a timeline of how galaxies evolve. Distance tells time, and shapes tell history. The galaxies in the deep field look different because the universe itself was different when their light began its journey. In that tiny square of sky, we are not only seeing far across space, we are seeing deep into the past. And the further back we look, the more the universe changes in front of us. Spirals, clumps, smears, pairs, faint streaks. When you look closely at the Hubble Deep Field, it does not show one type of galaxy. It shows many. Some galaxies in the image look familiar. They have clear spiral arms that curve around a bright center. These shapes resemble nearby spiral galaxies that we already understand, including our own Milky Way. Other galaxies look smooth and round. These are similar to elliptical galaxies, which contain older stars and little new star formation. But many of the distant galaxies in the deep field look different. They appear small and irregular. Some look clumpy, as if they are made of scattered patches of light. Others seem stretched or distorted. A few look like two bright spots close together, possibly two galaxies in the process of merging. This variety has often been described as a cosmic zoo. The word zoo fits because the image shows many types of systems at once. Each type reflects a different stage of galactic development. Nearby galaxies tend to appear more orderly. Spiral galaxies often have defined arms and stable central bulges. Elliptical galaxies appear smooth and symmetrical. But when we look deeper into space, we are also looking further back in time. The distant galaxies in the deep field existed when the universe was younger, and younger galaxies often look less organized. Many of the faint, high redshift galaxies appear irregular and clumpy. This supports the idea that galaxies grow over time through mergers and gradual accumulation of smaller systems. In the early universe, galaxies may have formed from smaller building blocks. These smaller systems collided and combined, slowly creating the larger spiral and elliptical galaxies we see nearby today. The deep field provides visual evidence of this process. Some galaxies in the image show signs of interaction. A few display double nuclei, meaning two bright cores appear within the same structure. This can be a sign of two galaxies in the process of merging. Others show faint tidal features. Tidal features are stretched streams of stars, pulled outward by gravitational interaction. These faint arcs suggest that galaxies were not isolated. They were influencing one another. Even in such a tiny patch of sky, the deep field reveals hints of a dynamic universe. Not every galaxy is interacting, of course. Many appear isolated and stable, but the mixture of orderly and chaotic systems suggests ongoing evolution. It is also important to note what the deep field does not show strongly. Because the field was chosen to avoid massive galaxy clusters, strong gravitational lensing is limited in this image. Gravitational lensing occurs when a massive object bends light from galaxies behind it, sometimes creating arcs or multiple images. In cluster fields, lensing can dominate the scene. In the deep field, the goal was to sample the background universe without the heavy influence of nearby massive clusters. This makes the image more representative of general galaxy distribution rather than extreme environments. Size is another clue. Nearby galaxies in the deep field appear larger in angular size. Their structure can be resolved more clearly. Distant galaxies appear smaller and often more compact. This is partly because of distance. The farther away a galaxy is, the smaller it appears in the sky. But it is also because early galaxies were physically smaller. Over billions of years, galaxies grow through mergers and star formation. So distant galaxies not only look small because they are far away, but because they were still developing. Brightness adds another layer to the story. Some galaxies shine clearly in the image, even though they are distant. Others are barely visible, sitting at the limit of detection. Color differences also reveal information. Bluer galaxies often contain younger, hotter stars. These systems may be actively forming new stars. Redder galaxies may contain older stars, or they may appear red because their light has been stretched by cosmic expansion. When you step back and look at the deep field as a whole, you see more than just thousands of dots. You see a record of growth. You see early galaxies forming and merging. You see mature systems that resemble galaxies in the present universe. You see structure emerging from what once looked like darkness. Shape is one clue. Color is another. brightness is another still. Together, they form a layered picture of cosmic evolution. And as we continue to examine fainter and fainter objects, we approach the limits of what the telescope can gather. Some galaxies in the Hubble Deep Field sit near the very edge of what the camera could detect. They are not bold spirals with bright arms. They are faint, extremely faint. Astronomers describe brightness using a system called magnitude. In this system, larger numbers mean fainter objects. The faintest stars visible to the naked eye under dark skies are around 6 magnitude. The faintest galaxies in the deep field approach 30th magnitude. That difference is enormous. Each step in magnitude represents a change in brightness. By the time you reach 30th magnitude, the object is billions of times fainter than what the human eye can see unaided. In simple terms, some of the galaxies in the deep field are about 4 billion times fainter than the faintest stars visible without a telescope. That is the level of faintness Hubble reached by stacking more than 100 hours of exposure. Without the long stare, those galaxies would remain invisible. This faintness matters because it reveals something important. The universe is filled not only with bright, obvious galaxies, but also with countless faint systems that contribute to the total population. Many of these faint galaxies are small and distant. Their light has traveled for billions of years before reaching Earth. Along the way, that light has spread out across space, making it weaker by the time it arrives. Some galaxies in the deep field appear as tiny red dots. Others are faint blue smudges. Even when their shapes are not clear, their colors carry clues. Color helps astronomers estimate redshift, which relates to distance. Very distant galaxies often appear redder. This is because the expansion of the universe stretches their light toward longer wavelengths during its journey. When light leaves a galaxy, it may begin as blue or ultraviolet light. But after traveling across billions of light years of expanding space, it can arrive at Earth shifted into the red or near infrared part of the spectrum. These very red galaxies in the deep field became candidates for high redshift systems. Some were estimated to have redshifts greater than 5. That places them in an era when the universe was roughly 1 billion years old. Color was not the only tool used to estimate distance, but it provided a statistical starting point. Bluer galaxies in the image are often closer or contain younger stars. Redder galaxies may be older systems or simply farther away. Brightness and color together help paint a timeline. The faintest objects in the deep field represent some of the earliest visible structures in the universe. They are small, dim, and often irregular. They sit at the edge of detection. Reaching 30th magnitude required extreme care. Every cosmic ray had to be removed, every background pattern corrected, every exposure aligned and stacked. The signal from those faint galaxies was barely above the noise. Even then, not all galaxies in that tiny patch were detected. The deep field image captured only the brightest fraction of galaxies within its volume. Many even fainter galaxies remain below the detection limit of that campaign. This realization led to an important shift in thinking. If thousands of galaxies appear in one tiny patch at that depth, and even more lie just below the detection threshold, then the total number of galaxies in the observable universe must be enormous. Later studies would revise galaxy counts upward as deeper surveys and new analysis techniques improved sensitivity. But even in 1995, the message was clear. The sky is not sparsely populated. It is rich beyond everyday imagination. The faintness of these galaxies also reminds us of human limits. Our eyes see bright nearby stars. Our telescopes, when given time, reveal distant galaxies. But even our best instruments have boundaries. The deep field was not the final word. It was the beginning of a deeper search. The hunger to see fainter and farther led to new campaigns in the years that followed. If 10 days revealed galaxies near 30 magnitude, what would 11 days reveal? What would hundreds of hours reveal? The Hubble Deep Field showed how faint the universe can appear. And that faintness inspired astronomers to push even further. HDF was the beginning, and the hunger for deeper images created the next step, the ultra-deep field. After the first deep field image was released, one question naturally followed. If 10 days revealed thousands of galaxies, what would happen if the telescope stared even longer? The answer came nearly a decade later. In 2004, the Hubble Space Telescope carried out an even deeper observation known as the Ultra Deep Field. This time, the telescope focused on a different tiny region of sky. The observing campaign lasted about 11 days of total exposure time, adding up to more than 1 million seconds of collected light. That is roughly 10 times longer than the original deep field's total exposure time. The principle was the same. Longer exposure means more collected photons. More photons mean fainter objects become visible. The result was dramatic. The ultra-deep field revealed around 10,000 galaxies within a similarly small patch of sky. 10,000, in a region only a few arc-minutes across. The deeper exposure pushed the detection limit further than before. Galaxies that were too faint to appear in the original deep field now became visible. Many of these newly revealed galaxies were extremely distant. Some had redshift values around 6 or higher. That places them in a time when the universe was less than 1 billion years old. The ultra-deep field began to approach what astronomers sometimes call the cosmic dawn. This term refers to the early era when the first generations of galaxies were forming. The image showed that galaxy formation was already well underway during those early epochs. Small, faint, irregular systems filled the frame. Compared to nearby galaxies, these distant systems looked compact and clumpy. Their appearance supported the idea that galaxies grow gradually through mergers and star formation over billions of years. The ultra-deep field also improves statistical estimates of galaxy density. By counting galaxies in that tiny region and comparing it to the area of the entire sky, astronomers could refine estimates of how many galaxies exist in the observable universe. Early estimates suggested on the order of 100 billion galaxies. Later studies, including analyses that accounted for faint systems below direct detection limits, suggested even larger numbers, possibly reaching into the trillions. The ultra-deep field demonstrated that the universe contains more structure than earlier surveys had revealed. And yet, even this was not the end. In 2012, scientists combined all available deep observations of the ultra-deep field region into a single composite image known as the extreme deep field. Instead of relying on one observing campaign, this image drew from years of archived exposures taken at different times. By stacking all those exposures together, astronomers produced one of the deepest optical images ever created at that time. The extreme deep field contains roughly 5,500 galaxies in an even smaller region. It reaches distances of up to about 13 billion light-years. This means the light from some galaxies in that image began traveling when the universe was only a few 100 million years old. Each deeper field revealed more faint galaxies. Each longer exposure pushed closer to the limits of what visible light telescopes can detect. These follow-up campaigns confirmed an important lesson. The original deep field was not an isolated surprise. It was a glimpse of a much larger pattern. The sky is filled with galaxies in every direction. When you increase exposure time, more galaxies appear. When you push sensitivity further, even more structure emerges. The deep field opened a door. The ultra-deep field widened it. The extreme deep field pushed it even further. Together, these images changed our sense of cosmic scale. What once appeared empty is now understood as layered with structure across billions of light years. The deeper we look, the more we find. And with each deeper observation, the same idea returns. Darkness is not absence. It is distance waiting to be measured. After the original Hubble Deep Field was released, astronomers around the world felt the same reaction: awe. But after awe comes curiosity. If 10 days of exposure revealed roughly 3,000 galaxies in a tiny patch of sky, what would happen if the telescope stared even longer? That question led to the ultra-deep field. In 2004, the Hubble Space Telescope carried out an even more ambitious observing campaign. This time, instead of about 100 hours of total exposure, the telescope gathered more than 1 million seconds of light. 1 million seconds equals about 11 full days of exposure time. To compare clearly, the original deep field used roughly 100 hours. The ultra-deep field used about 1,000 hours. 10 times deeper. 10 times longer. The region chosen for the ultra-deep field was different from the first deep field. It was located in the southern sky. Like the original, it was carefully selected to avoid bright stars and nearby massive galaxy clusters. The goal was still to study the distant background universe without interference from strong foreground objects. The strategy remained simple. Point the telescope at a very small, dark patch of sky. Collect light for as long as possible. Then stack the exposures. The longer exposure time made a dramatic difference. The ultra-deep field revealed about 10,000 galaxies within a similarly tiny region of sky. 10,000 galaxies in an area only a few arc-minutes across. Many of these galaxies were so faint that they had not appeared in the original deep field. The deeper exposure pushed the detection limit to new extremes. Some of the galaxies identified in the ultra-deep field had redshift values around 6 or even higher. A redshift of 6 means the light began its journey when the universe was less than 1 billion years old. Considering that the universe is now about 13.8 billion years old, that means we are seeing those galaxies as they existed more than 12 billion years ago. This pushed observations toward what astronomers sometimes call the cosmic dawn. The cosmic dawn refers to the era when the first generations of stars and galaxies were forming after the Big Bang. Before that time, the universe was dark and filled mostly with hydrogen gas. As the first stars ignited, they began to light up space and change its structure. The ultra-deep field did not capture the very first stars directly, but it came closer than any previous optical image. Many of the galaxies in the ultra-deep field appear small and irregular. Their shapes are often clumpy rather than smooth. This suggests active star formation and frequent merging events. Compared to nearby galaxies, which often have clear spiral arms or rounded elliptical shapes, these distant galaxies look younger and less organized. This supports the idea that galaxies grow over time. In the early universe, galaxies were smaller and more chaotic. Over billions of years, they merged with other systems, formed new stars, and developed more stable structures. The ultra-deep field also refined galaxy counts. If roughly 10,000 galaxies appear in one small patch at this depth, then the total number across the entire sky must be enormous. Even so, astronomers realize something important. Even 1,000 hours of exposure does not reveal everything. There are still galaxies too faint to detect, even in the ultra-deep field. The deeper you look, the more you find. And with each increase in exposure time, the number of detected galaxies grows. This lesson was powerful. The original deep field proved that darkness hides structure. The ultra-deep field proved that even deeper darkness hides even more. But astronomers were not finished. If one long observing campaign could reveal 10,000 galaxies, what might happen if you combined many years of archived exposures into a single image? That idea led to the next step. Ultra-deep led to extreme deep, combining years of data into one single image. Sometimes the deepest image does not come from one long stare. Sometimes it comes from patience across decades. After the ultra-deep field in 2004, astronomers realized something important. Over the years, the Hubble Space Telescope had returned to that same region of sky many times for different scientific programs. Each visit added more exposure time. Each exposure gathered more photons. Instead of letting those separate observations sit alone in archives, scientists asked a new question. What if we combine all of them? In 2012, researchers released an image known as the Hubble Extreme Deep Field, often shortened to XDF. This image was not based on one observing campaign. It was built from years of archived exposures taken in the same ultra-deep field region. By carefully aligning and stacking all available deep images of that area, astronomers created one of the deepest optical images ever produced at that time. The exposure time added up to effectively thousands of hours when all archival data were combined. The XDF focused on a smaller region within the ultra-deep field area. Even though the area was smaller, the depth was greater. The stacking process was more extensive, and detection criteria were more conservative to ensure reliability. The result was an image containing roughly 5,500 galaxies within that tiny region. NASA described the XDF as reaching distances up to about 13 billion light-years. That means some of the galaxies visible in that image are seen as they existed only a few 100 million years after the Big Bang. These galaxies are among the earliest known visible structures in the universe at the time the image was released. The XDF did not simply add more galaxies. It improved clarity and depth. Some galaxies that appeared faint or uncertain in the ultra-deep field became clearer in the XDF. Other extremely faint galaxies emerged for the first time. By stacking years of data, astronomers reduced noise and improved signal-to-noise ratios. This allowed them to detect objects that were previously buried below detection thresholds. The XDF reinforced a key lesson from the earlier deep fields. There is no sudden edge to structure. The deeper you look, the more galaxies appear. Even after 11 days of exposure in 2004, more galaxies were still waiting just below the limit. When the exposures from many programs were combined, even fainter systems came into view. The XDF also strengthened the statistical understanding of galaxy counts. Although it covered a smaller area than the original ultra-deep field, it confirmed that galaxy density remains extremely high at faint brightness levels. This helped refine estimates of how many galaxies might exist across the entire observable universe. By 2012, it was clear that earlier estimates of about 100 billion galaxies might be too low. Later research suggested that when accounting for ultra-faint galaxies below direct detection limits, the total number could reach into the trillions. The XDF acted like a core sample of the universe. It did not show everything, but within its tiny area, it revealed layer upon layer of structure across cosmic time. Each faint dot in the image represents billions of stars. Each tiny smudge represents a galaxy evolving over billions of years. And all of them fit inside a patch of sky no larger than a grain of sand held at arm's length. The XDF marked a turning point. It showed the power of archival data. It demonstrated that combining years of careful observation can push limits without building a new telescope. But it also highlighted something else. Even this deepest optical image still had limits. Many galaxies remain too faint for Hubble's visible light instruments to detect. To push further into the early universe, astronomers would need new tools. Deeper images shift our sense of how many. And once the numbers grow into the billions and trillions, a classic question returns. If the universe is filled with galaxies in every direction, why does the night sky still look dark? Before we scale up the math, let's quickly revisit arc minutes. Astronomers measure the sky in angles. One full circle around you is 360 degrees. Each degree is divided into 60 smaller units called arc minutes. The full moon appears about 30 arc minutes wide in the sky. The Hubble Deep Field was only about 2.6 arc minutes across. That means it was less than 1/10 the width of the moon, a tiny square in a very large sky. A very large sky indeed. Astronomers measure the whole celestial sphere as about 41,253 square degrees. Earlier in the video, we estimated how many deep field patches could tile the sky and arrived at a number closer to 24 million. That estimate used the full geometric square of 2.6 arc minutes by 2.6 arc minutes. However, many NASA summaries describe the deep field's effective science area as about 0.0011 square degrees, which accounts for the usable imaging region rather than the simple square outline. When we use that smaller effective area, the number increases to roughly 37 million patches across the sky. The difference comes from how the field's exact usable area is defined, not from a change in the size of the sky itself. If you divide the entire sky by 0.0011 square degrees, you get roughly 37.5 million such patches. 37.5 million grain of sand squares could tile the entire sky. Now multiply. If one patch contains about 3,000 galaxies, and there are 37.5 million patches, that equals approximately 112.5 billion galaxies. That estimate comes directly from simple scaling. 3,000 times 37,500,000 equals about 112,500,000,000. Over 100 billion galaxies. And that calculation uses the original deep field count, which only included galaxies bright enough to be detected in that exposure. It does not include galaxies too faint to see. This is where things become even more interesting. Later studies suggested that the deep field and even the ultra-deep field only detected a fraction of the total galaxies within their volumes. Some research indicates that Hubble may have seen only about the brightest 30% of galaxies present in those regions. That means many faint galaxies remained below the detection limit. When astronomers account for these ultra-faint galaxies using models and deeper surveys, estimates of the total number of galaxies in the observable universe rise significantly. In 2016, research led by Christopher Consoli suggested that the true number of galaxies could be 10 times higher than earlier estimates. Instead of 100 billion galaxies, the observable universe might contain 1 to 2 trillion galaxies. That is 1,000 billion galaxies. Each galaxy contains on average billions to hundreds of billions of stars. The Milky Way alone contains on the order of 100 billion stars. If many galaxies are similar in size, the total number of stars in the observable universe becomes almost impossible to picture. Now step back to the grain of sand image. In that tiny patch of sky, there are thousands of galaxies. Across the whole sky, there may be hundreds of billions or even trillions. And this is only the observable universe. The observable universe is limited by how far light has traveled since the Big Bang. Beyond that boundary, there may be even more galaxies that we cannot see. The math is simple multiplication, but the meaning is not simple at all. A small square of darkness holds thousands of galaxies. Millions of those squares fill the sky, and each galaxy holds billions of stars. This scaling process turns a tiny image into a cosmic census. The deep field acts like a sample. Just as a scientist might examine a small core of rock to understand a mountain, astronomers examine a small patch of sky to understand the universe. The deeper the image, the more accurate the estimate. But there is another important detail. The sky does not look crowded to our eyes. When we look up at night, we see darkness with scattered stars. We do not see trillions of galaxies shining. So how can the universe be so full and yet appear so dark? When numbers grow this large, a classic question returns. If galaxies fill space in every direction, why does the night sky remain black instead of glowing white? That question is not new. It has a name. And the deep field makes it feel more real than ever. It is called Olber's paradox. If galaxies fill space in every direction, why does the night sky look dark instead of bright? This question is known as Olber's paradox. The paradox is simple to state. If the universe were infinite, eternal, and evenly filled with stars and galaxies, then every line of sight in the sky should eventually end on a star. The entire sky should glow as brightly as the surface of the sun. But it does not. The sky is mostly dark. For centuries, this seemed confusing. The Hubble Deep Field makes this question feel even stronger. When we look deeply enough, even a tiny patch of sky contains thousands of galaxies. That suggests the universe is packed with structure. So why is the night sky not blazing with light? The answer comes from several key ideas in modern cosmology. First, the universe has a finite age. The universe is about 13.8 billion years old. Light travels at a finite speed. That means we can only see objects whose light has had time to reach us. If a galaxy is so far away that its light has not yet arrived, we cannot see it. This limits the observable universe. Even if space extends farther beyond what we can observe, we are confined to a sphere defined by how far light has traveled since the Big Bang. Second, the universe is expanding. As space expands, light traveling through it stretches. This stretching increases the wavelength of the light. It shifts visible light toward longer wavelengths, such as infrared. This process is called redshift. Very distant galaxies may be emitting visible light when it leaves them, but by the time that light reaches Earth, it has been stretched into wavelengths that the human eye cannot detect. So even though galaxies fill space, much of their light has shifted beyond visible range. Third, the universe was not always filled with shining stars. There was a time after the Big Bang when stars had not yet formed. During that era, called the Cosmic Dark Ages, there were no bright stars lighting up the universe. Because the universe has a finite age, there has not been enough time for light from every possible star or galaxy to reach us. These three factors resolve the paradox. The sky is dark because the universe is not infinitely old. The sky is dark because the universe is expanding. The sky is dark because light from very distant galaxies has been stretched out of visible wavelengths. The deep field helps make this real. In that tiny patch of sky, thousands of galaxies exist, but they are incredibly faint. Many are billions of light years away. Their light has been dimmed by distance and stretched by expansion. Even if you added up all the light from those galaxies in the deep field, it would not make the sky bright to our eyes. The total brightness of the night sky is limited. Each galaxy contributes only a small amount of light per unit area in our sky. And much of that light arrives in wavelengths outside human vision. So the darkness of the night sky is not evidence of emptiness. It is evidence of cosmic history. It tells us that the universe began at a specific time. It tells us that space is expanding. It tells us that light travels at a finite speed. The paradox dissolves when we understand the physics. And yet the emotional effect remains powerful. When you look up at the night sky, you see blackness dotted with stars. But hidden inside that blackness are countless galaxies, too faint and too distant for your eyes. Darkness becomes a clue rather than a void. And once we understand why the sky looks dark, the final question becomes more personal. If empty space is filled with galaxies beyond what we can see, what does emptiness really mean? That is where the story of the deep field leaves us. Not with a contradiction, but with a new definition of darkness. When you look up at the night sky, it feels calm, dark, almost empty. But now you know something different. That darkness is not empty at all. In a patch of sky smaller than a grain of sand held at arm's length, the Hubble Deep Field revealed thousands of galaxies. Later, images revealed even more. 10,000. Then thousands more layered deeper still. And if one tiny square holds thousands of galaxies, and millions of those squares tile the sky, then the universe is far richer than our eyes can ever show us. The blackness we see is not a lack of structure. It is distance. It is time. It is light that has traveled billions of years and grown faint along the way. The deep field changed something simple but profound. It changed the meaning of the word empty. Empty space is not empty. It is filled with galaxies too far, too faint, or too red-shifted for our eyes. And even Hubble, with its 10-day stare, saw only the brightest fraction of what is really there. Beyond its limits, more galaxies wait. Beyond those, even more. The night sky remains quiet to us. But inside every quiet patch, deep time and deep light are still moving, still traveling, still telling the story of a universe far larger than we once imagined. And all of it is hidden inside the darkness we casually call empty.